to a different topic. We'll be doing an algebra review, and our topic for today is going to be laws of indices. So today our lesson objectives include defining and identifying the terms index, base, expanded form, and index form. Convert expressions from index form to expanded form and vice versa. And define and apply the multiplication, division, and zero law to simplify expressions. So for those of you that haven't done laws of indices yet, this will be an introduction lesson for you. And for those of you that have done it, this will just be a recap. And for mathematics, you can never have too much practice. So let's look at a quick video that basically recaps the little information that you would have learned about indices in junior high, and you're going to see now how we are going to build on that information.
Hi, I'm Lucy, and in this video we're going to look at indices. See this small floating number here and here? This is an index number, or a power, and the plural of index number is indices, hence the title of this video. It just tells us how many times a number or letter has been multiplied by itself. So 3 squared means 3 multiplied by 3, twice. X cubed means x multiplied by x multiplied by x, so 3 times. And 2y to the power of 4 means 2y multiplied by 2y 4 times. You know how in algebra we have silent ones, so we don't write 1a, we just write a. Something without a power, so b for example, really means b to the power of 1. But the 1 is silent, so we don't write it. Can you answer these 3 questions? Pause the video, work out the answer, and click play when you're ready to check. Did you get them right? So that's the admin part covered. Now we are ready to look at the laws of indices. These laws, or rules, make complex sums which involve powers much easier, and they are also essential for understanding lots of algebraic processes. Watch our Law of Indices videos to discover more.
Okay, if you are okay, let's move on. So let's look at a quick question and make sure that you understand. Is the following expression in index form or expanded form? Yes, it is in expanded form. Now, what if I ask you to write this in index form? How would it look? And you can also type that in the chat box. How would this particular expression look in index form? I'm seeing some answers come. Very good. So it would be 2 to the power of 3 times 3 to the power of 2 times 4. Now, I've noticed some people are correctly it's a bit tricky when you're typing it out, saying that if you're on a phone, your phone doesn't allow you to put in the power, or if you're on your computer, it really doesn't allow you either. So another way you can show that something is an index is by using, if you press shift and the number 6, this will come up. So something like this is read 2 to the power of 6. This little symbol right here indicates that something is being something, let me change it to 3, like the example. This little symbol right here indicates that something is, the number behind it is a power. So just for some of you that weren't sure, I see some of you went the smart way and just typed out the word completely and put cubed. That is fine since you're typing, but you can use this particular feature right here. So 2 to the power of 3 times 3 to the power of 2 times 4. Okay, so if you had something that looks like this, you are correct. And so I'm okay, let's continue. So just a quick reminder before we jump into our 3 laws for today. If you remember from learning the basics in algebra, AB is the same thing as A times B. So in algebra, when you see numbers or letters written closely together like this with no symbol or anything in between, that is to tell you that multiplication is happening in between these numbers or these letters. So if you see AB, that means A times B. And if you see 5A squared B, that means 5 times A times A times B. So whenever numbers and letters are written together like this, multiplication is going on in between. Or whenever you see 2 letters written back to back like this, multiplication is still going on. It's just a shorter way to write these expressions because you don't want to have to write this out every time. So let's continue. So now moving on to the laws of indices. So if you see either one of these topics, laws of indices, laws of exponents, laws of powers, they all mean the exact same thing. So if you see laws of indices, but then you need to write laws of powers on the board, it's still the same thing. And these are the 3 laws of indices that we will be looking at today, as stated in the objectives. I'm going to tell you what you need to write. So have a pen handy. So a quick reminder, always remember that the laws of indices can only be applied when we have numerical or algebraic, meaning variable expressions with the same base. So in order for you to group or put something in index form, it has to have the same base. And I think most of you understood that from the previous example where we had to put the 2, the 3, and the 4, that expression, where we had to put that in index form. So let's look at the multiplication law, and you can write this down. When we multiply quantities with the same base, we add their indices. So I need you to put emphasis when you're writing. Put emphasis on add, please. That is what's most important here. When multiplying quantities with the same base, we add their indices. And so this is the rule. This is how it looks. So if you have an A, M, and N, A, M, and N can be any numbers. So you'll see in the examples given, they can either remain as letters or they can be numbers. But this, we give you the letters just so that you can get a general idea of the rule. So if you have A to the power of M times A to the power of N, all you do is you add the exponents. You keep the same base. So if your base was 3 here and your base was 3, you will have 3 to the power of m plus n. And then obviously if m and n are numbers, you would just add the numbers to simplify. But this is the basic and general rule for the multiplication law. Give you about 10 more seconds to write this. Okay, so let's see how this law works.
What's up again, and welcome to the next lesson in our unit on the laws of exponents. So let's target our thinking by asking the question, how can we multiply powers with the same base? Okay, so what does that mean? For example, what if we wanted to multiply 3 to the second power by 3 to the third power? Both of these have the same base, which is 3. So with this in mind, let's go ahead and try and simplify this. Let's start off by rewriting each term in a broken down form, as in 3 to the second power is 3 times 3, and 3 to the third power is 3 times 3 times 3. And again, we're multiplying each of these two things together. Okay, now notice here down below that we have 3 being multiplied by itself 5 times. Another way of saying this is 3 to the 5th power, or 3 to the power of 5. Now the question is, how did we use those exponents of 2 and 3 with the same base and end up with a 5 exponent in our simplified answer? You may have noticed that 5 is equal to the sum of 2 and 3. And this turns out to be one of the laws of exponents, which says that whenever you multiply 2 or more exponents with the same base, so for instance, some value x raised to the power of a times the same value x raised to the power of b, the rule is that you take those two exponents and you add them together, which we broke down in that first example. And now we can apply that law to one final example. Instead of variables as exponents, let's replace them with real numbers. If we had something like x to the 5th times x to the 7th, again, since the bases are the same, we can simplify this by adding the two exponents, 5 plus 7, which results in a simplified answer of x to the 12th. So in conclusion, whenever multiplying 2 or more exponents with the same base, you just add them up and you're good.
Cool.
So thank you again for visually exploring this concept with us, and please feel free.
So let's simplify the following expressions. So our first example is 2 to the power of 4 times 2 to the power of 3. Because this expression, the parts of the expression, because they have the same base, which is 2, we can apply the multiplication law and add the indices. So the next line is going to be 2 to the power of 4 plus 3. And so my final answer is going to be 2 to the power of 7. And so in this case, since we're only focusing on the indices, we can leave the answer just like this. Okay, let's look at another example with some letters. So I have x to the power of 3 times x to the power of 5. They both have the same base, so I can go ahead and add their indices. So always check to see if they have the same base, and then once they have the same base, you can go ahead and add the indices. Very good. I see some persons responding in the chat. Let's look at another example. So this one is a little bit more complex. We have numbers and letters mixed together, but the steps and the rules are still the same. So because 3 and 2 don't have the same base, well, and their exponents are 1, we don't really add the exponents on the 3 and the 2 because the bases aren't the same. However, because we're simplifying, we can just go ahead and multiply them. So it'll be 3 times 2 times x, and the x's have the same base, so I can add their exponents. So my final answer is going to be 6x to the power of 9. So if you have any questions about these examples, you can send them in the question and answer feature. And if not, let's move on. I don't see any questions, so I'm assuming that this was clear. Examples were clear. Everything, all the steps are clear. You can send yes or a thumbs up. Okay, excellent. So these are some quick practice questions. I'm going to give you 2 minutes to try these questions. You can write them down on whatever you're writing on. I'm going to give you 2 minutes. I'm going to put on a timer. And then we will go through the answers together. So don't send no answers yet. Just work on it. When the timer is up and we go through them, then you can send your answers. Okay, about 30 seconds left. Okay, so as the answers appear, I will explain and you can then check to see if your answer was correct or not. And at the end, I will ask you to say how many out of the 4 did you get correct. So don't send any answers in the chat. So let's look at the first one. We have 3 to the power of 2 times 3 to the power of 5. And so the answer was 3 to the power of 7. Because they have the same base, I can add and apply the multiplication law of indices and add the indices. Next example, we have y to the power of 6 times y to the power of 2. So once again, because they have the same base, I can just add the indices. So it'll be y to the power of 8. Third example, I have numbers and letters. So when you have numbers and letters, you can simplify the numbers, or in this case, the coefficients. That's what the numbers in front of letters are called, coefficients. You can multiply them. So 2 times 4 is going to give me 8. And because the x's have the same base, we can add the exponents. So my final answer is going to be 8x to the power of 4. See, both of them have the same base, which is a, but notice we have a silent indice on my last a, and that silent indice is 1. So 4 plus 1 will give me a to the power of 5. Don't forget, when you see a letter by itself, the coefficient, which is the number in the front, is 1, and the index is 1. Remember, not just because it isn't there doesn't mean that it doesn't have an indice. Once again, it'll come with practice. You have to keep remembering the law and remembering how to apply it. So with that being said, let's move on. Let's move on to the division law. And I want you to write this down, please. When we divide quantities with the same base, we subtract the denominator index form from the numerator index form. So in this case, we have words like denominator and numerator because we know that writing fractions can also represent division. So for the division law, sometimes it may come in the form with the division symbol, or sometimes it may be written as a fraction. But you must remember that fractions also mean to divide. So once the bases are the same for division and you're dividing, you just subtract the exponents. So with multiplication, you add the exponents. With division, you subtract the exponents. So this is the rule. Okay, let's watch a similar video to the multiplication.
Into it. Hello again, and thank you for stopping by and checking out this lesson from our series on the laws of exponents. And as always, we start off with a question, and that is, how can we divide powers with the same base? So let's continue to explore this concept by looking at an example. Imagine dividing 5 to the 7th power by 5 to the 4th power. Again, they both have the same base of 5. So let's go ahead and expand the numerator and denominator. 5 to the 7th power is 7 5s being multiplied together, and 5 to the 4th power is 4 5s being multiplied together. Now, by applying our understanding of fractions, we can line up the numerator with the denominator and see that we have a match of 4 5s on the top and the bottom that can be canceled out, since any number divided by itself is just 1. And what we're left with is 5 times 5 times 5. And another way to write this is 5 to the 3rd power.
Cool.
So the question here is, how did we use those exponents of 7 and 4 to result in a value of 3 in our simplified answer? You may have noticed that 7 minus 4 is equal to 3. And this relationship is going to actually be a law for exponents that says that whenever you divide 2 or more exponents with the same base, such as x to the a divided by x to the b, is equivalent to x to the difference of the numerator and the denominator. For example, if we replaced the a and the b with actual numbers, in this case x to the 9th power being divided by x to the 6th power, that quotient would be equivalent to x to the 9 minus 6, and we know that 9 minus 6 is 3, so our simplified form is x to the 3rd power. So in conclusion, whenever we divide two exponents with the same base, you simply subtract the exponents to get a simplified form. And that's all there is to it. This should be a good start, a good conceptual start to your studies of the...
The division law is quite simple because really it's the opposite. So let's look at some examples. So express each of the following quotients in index form. So here we have 5 to the power of 9 divided by 5 to the power of 8. So because they have the same base, we can just go ahead and subtract the bases now. And so my answer will be 5 to the power of 1, which is the same thing as 5. Let's look at another example. Now this example is written in the fraction form, however, it's still division. So we have a to the power of 12 as our numerator and a to the power of 5 as our denominator. And so because fractions mean divide and they have the same base, I can just subtract my indices. So 12 take away 5 will give me a to the power of 7. And our final example is a bit more complex. We have several letters here with different exponents, but don't get scared when you see something like this. All you do is you group the letters that are the same together, because remember, you can only apply these laws if the bases are the same. So for example, because I'm dividing here, in order for me to subtract the base on this p, subtract the exponent, on the p, I have to find another p with an exponent to subtract them. So the p's will go together. So it'll be p, show you how it looks. It'll be p to the 5th power, take away 3. The q's will go together. So it'll be q to the power of 3, subtract 2. And the powers of the r will go together. So it'll be r to the power of 4, take away 1. And then you just simplify. So the final answer will be p squared, q to the power of 1, r cubed. Or if you want to rewrite it, where q doesn't have, where the 1 on the q is silent, as we said, your final answer will be p squared q r to the power of 3. Does this last example make sense? Yes or no? Excellent. So I'm seeing mostly yeses. So one more time to reiterate. Firstly, you pay attention to the operation that's happening. You want to pay attention to see if it's multiplication or division. If you have more than one letter, you just make sure that you group the letters that have the same basis. You group them together. So for example, with p to the power of 5, I shouldn't have subtracted 2 because 2 has a base of q, and p and q are two different letters. The bases aren't the same, so I can't do that. Only where the bases are the same, you subtract their exponents. So let's do some. So try these ones. Oh, sorry. Try this one. This one is quite easy. So we have 4 to the power of 7 over 4 squared. Okay, so if you got 4 to the power of 5, then you are correct. Let's look at another example. I'll give you a few seconds before I reveal the answer. Okay, so because we're dividing, if you got t to the power of 11, then you are correct. So you subtract the indices. So yes, I see someone got a little frazzled because of the big numbers. Don't worry about the big numbers. The rules are still the same. The same laws will apply. As long as the bases are the same and you're dividing, you subtract the exponents. Look at another example. So I'll give you a few seconds. Okay, I see some answers coming in. Let's look. So our answer is 4x to the power of 7. So keep in mind, when we have coefficients, which are the big numbers in the front of our letters, these numbers will be divided as you would regularly divide whole numbers or integers. You don't subtract these numbers. These numbers will be divided. You only subtract the exponents. And so 9 take away 2 gave us the 7, and 12 divided by 3 gave us 4. Same thing as if this was division. If the multiplication, if this was multiplication, it would be 12 times 3. So let's look at our final example. I'll give you a few seconds. Okay, let's reveal our answer. Our answer is a to the power of 2. So remember, the single letter A, even though you don't see an exponent there, the exponent there is always 1. So it'll be a to the power of 3, take away 1, and our final answer will be a to the power of 2. Okay, any final questions on this? I don't see any. 1 second. Okay, let's move on. So our final law, and this law is pretty much the easiest law of them all, is the zero law. So any number except 0 raised to the power of 0 is equal to 1. So this is the rule. Anything that you raise to the power of 0, except the number 0 itself, will always be equal to 1.
So something that shows up in classes is you'll get something like x to the 0. And your teacher will say x to the 0 equals 1. Or maybe it's a number, 3 to the 0, or really anything you want. You can make it as complicated as you like. All of these things all equal 1. And a good question is, why? Why does that equal 1? Did someone just decide that's what it's going to be? And the answer is no. We can show that it has to equal 1. So the easy way to see this is just to start out by taking whatever number it is. Let's say we're doing x, and write x over x. Well, of course, we know x over x is just 1. But another way we can write this, right, is this is x to the 1 power over x to the 1 power. And if we're dividing two variables, we can go ahead and just subtract their powers, the 1 on top minus the 1 on bottom. And of course, 1 minus 1 is 0. So there you go. We just showed that x to the 0 equals 1. So there we did it for x. Let's go ahead and do it again for 3, just to show that it works exactly the same way. So 3 over 3, that obviously equals 1. On the other hand, I can write that as 3 to the 1 power over 3 to the 1 power, and then I can take the top power minus the bottom power, which gives me 3 to the 0. And at this point, it should be clear that there's nothing special about x or 3. I could put whatever I want there and that would work. Except, the one exception to this rule is 0. So 0 to the 0 does not equal 1. In fact, 0 to the 0 is undefined, which is just a way of saying that we can't say it equals any number. It equals no number. So let's see why that's the case. So we start out the same. We do 0 over 0. The problem is, you remember from your classes that you cannot divide by 0. So 0 over 0 not only does not equal 1, it doesn't equal any number. It's undefined. So already we're stuck, and we can't do the same process. So this is why 0 to the 0 is not equal to 1. I hope that helps, and if you have any questions or things you'd like me to talk about, please feel free to post a comment below, and I'll be sure to get to those. Thanks, and have a good one.
So any number raised to the power of 0, except the actual number 0 itself, will be equal to 1. So let's look at some examples. So if we have 2 to the power of 0, my answer is going to be 1. Another example, if we have the letter S to the power of 0, my answer is still going to be 1. If we have 19,993,398 raised to the power of 0, the answer is still 1. And final example, if we have open bracket xy, close bracket raised to the power of 0, my answer is still going to be 1. So anything except 0 raised to the power of 0 will be 1. And so this is our last law for today. Now, we don't have time to go over the other practice questions, but I will include it in the beginning of tomorrow's, well, no, I don't teach tomorrow. Tomorrow's Wednesday. In the next lesson, which will be on Thursday, the practice questions will be included in the beginning part of that lesson. Okay, so I'm seeing a comment. Someone, so a lot of you may be trying to figure out how, what is the proof behind anything raised to the power of 0 is equal to 1. So in the links provided that I will post again in a few seconds. Now, so included in these links will be the recap video, all of the videos that were shown, as well as the video for the 0 law that we didn't get to watch due to time, and then another link that says more info. That link is a written explanation on why the zero law is what it is. And then there is a Jeopardy practice game for those who want to practice at home. Also, my email will be provided for those of you that still have questions. I'm going to resend it now. And so that basically wraps up our lesson on the beginning of the laws of indices. So next lesson, we're going to be looking at some more laws because there are more. It's about 7 or 8 of them. And these were the first 3 laws. So check out the links that were provided to recap on what we did today. And I think you have another lesson left. So if you have questions, you can just send me an email and I'll be happy to help. Continue to be safe and have fun in your next lesson.
Hello students, I'm Miss Combo.
And I'm Conk Boy.
And we are going to explore the wonderful world of figurative languages. You want to learn more? Let's go! Okay kids, let's look at this figurative language. We are focusing on
Metaphor, 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 metaphor.
That's right, Conk Boy, metaphor. Why do we use figurative languages? Well, we use them to enhance our writing and to give our readers a vivid picture. What is a metaphor? A metaphor is a figure of speech that compares 2 things by saying one thing is the other. Here is the breakdown. Instead of writing, he is smart. Write, he is a shining star. This means you are comparing the boy to a shining star that is bright, meaning he is intelligent. Instead of writing, Megan's room is filthy. Write, Megan's room is a pigsty. You will be comparing Megan's room to a pigsty. A pigsty is dirty and filthy. Let's identify it in a text. I sat in my class excited about the lesson. My teacher walked in shortly with loads of work. She scanned the room in shock. I thought to myself, my classmates are a bunch of wild animals. Did you spot the metaphor? If you said, my classmates are a bunch of wild animals, you are absolutely correct. The 2 things being compared here are the classmates and wild animals. Wild animals jump around and make loud noises. This comparison tells me that my classmates were jumping around and making loud noises. Now you try it. Ray is a sweet and kind girl. How can you make that a metaphor? Let's think of something that is sweet and compare Ray to it. It can be an angel or a cupcake. So, Ray is an angel. Ray is a cupcake. Let's recap. A metaphor compares 2 things. Do not use the words like or as. Use linking verbs like am, is, are, was, or were. Wasn't that fun, Conk Boy?
Yeah!
Did you enjoy it, students? Stay tuned for the next figurative language.